In this section, we learn how to graph rational functions. Rational functions are functions that can be written in the form of a p of x over q of x, I mean ratio of two polynomials. And as we define polynomials are functions that can be written in this form or this form. It's the same form, but I just changed the index from n to m for the denominator and the coefficients just to distinguish between those two polynomials. And the power n should be non-negative integer. That means we should not have any negative power, we should not have any fractional power, and so on for the polynomials. And the denominator should be different from 0, because if it's 0, then the graph is discontinuous at x, where q of x is equal to 0. Now some examples of rational functions. F of x here is a rational function because the numerator is a polynomial, the denominator is polynomial, so this is rational function. The function g of x is also rational function because the numerator is a polynomial, the denominator is polynomial, so it's rational function. Now let's start with one of the simplest rational functions. F of x equals 1 over x. Let's graph this function. In order to graph this function using the techniques that we learned before, we need to choose some values of x like -2, -1, 0, 1, and 2, and find the corresponding values of y. So when x equals -2, we get -1/2. When x equals -1, we get -1. When x equals 0, the denominator cannot be 0, so we don't have corresponding values because the function is not defined at that point. When x equals 1, we get 1. X equals 2, we get 1/2. Now we plot these points in the xy plane. So we have -2 and -1/2 here at this point, and -1 with -1 this point here. 0 is not defined. 1 gives 1. And 2 gives 1/2. So when we graph these points, we get a graph like this. The graph looks like this from here and looks like this from here. So this is a graph of the function f of x equals 1 over x. As you can see, when x equals 0, we have the graph. When x equals 0, the function is not defined, so we don't have a graph here, we don't have a graph here, and that line x equals 0 is called the vertical asymptote. As you can see, the graph gets closer and closer to that asymptote, but it cannot touch that asymptote. And from here, the graph gets closer and closer as x to that vertical line as x approaches 0. And we'll define vertical asymptotes later, but for now this is vertical asymptote. There's another asymptote here, is the horizontal asymptote. As you can see, the graph cannot intersect here. Actually it can intersect for some problems, but for some rational functions, it can't touch or intersect the horizontal asymptote. But for our graph here, it just gets closer and closer to the horizontal line, but it doesn't touch that line. So we have some behavior here. We can study this behavior by saying that this is a horizontal asymptote, so we can define the vertical asymptote by saying that the vertical asymptote can be defined as a limit of the function as x goes to some point here, 0, equals infinity. When x goes to 0 from the right here, it goes to infinity. And actually I used limit definition here, but if you don't want to use some calculus notation, which is the limit, is one of the basic calculus notation. You can just describe it this way. You can say that the function, I mean the curve of the function, goes to plus infinity here as x approaches 0 here from the right, and let's take absolute value of fx, and the absolute value of fx, or the absolute value of f of x goes to infinity. If we take absolute value of f of x here, we don't need to consider the negative part. We just consider the right part here, because x is, when we take absolute value, we get just positive values. So as x gets closer and closer to 0 from the right, the graph of the function goes to infinity, or approaches infinity. We'll elaborate this when we discuss the asymptotes, or the mathematical setting of asymptotes, but this is just an example. Now, if we have function like f of x equals 1 over x plus 2 squared minus 1, you know that you start with the basic function. If we want to graph this, the basic function is 1 over x, which is the function that we already graphed, and then you add 2 to x, the variable. That means we make shift to the left 2 steps, and that means we get a graph like this one. And then we subtract 1 from the function. That means we bring it down 1 unit. So it looks like this. And actually for the second part, it should be here, because the function here, it's not only 1 over x, it's 1 over x squared. So that means we don't have the negative. If this is just 1 over x, then that's it. Let's use that case when the denominator is just 1 over x plus 2, so that we get same, we get our results here. So this is 1 over x, so the basic function is 1 over x, and then we add 2 to the variable x. That means we make shift to the left 2 steps, or 2 units. We get this function. This is 1 over x plus 2, and then we make shift down by 1 unit, so we get this graph. Now we can graph, but this graph is not actually accurate. We can use many features of rational functions to get better graph of rational functions. So we will learn how to do that in this section. So we'll start with the definition of asymptotes, because asymptotes play a very important role in graphing rational functions. So what do we mean by asymptotes? For asymptotes, we have 2 types: vertical asymptotes, and in this case, absolute value of the function goes to infinity as x goes to or approaches some value. And here in this case, x equals a is a vertical asymptote. I will use this abbreviation, VA. As we've seen before here, the x equals 0 is the vertical asymptote. And actually, the vertical asymptote is the 0 of the denominator in general, but if the function is written in the simplest form, or the lowest term. But if the function is not written in the lowest form or lowest term, we need to distinguish between 2 things: vertical asymptotes and whole, as we'll see later. So we have vertical asymptotes, and we have horizontal asymptote. We get a horizontal asymptote if the function approaches some value, let's call it b, as x goes to infinity. For example, for this for 1 over x, when the function is 1 over x, as you can see, when x goes to infinity, when x goes to positive infinity, the graph of the function goes to 0, approaches 0. So 0 is b here, so the graph of the function f of x approach b as x goes to infinity. So an example of this is the function f of x equals x minus 1 over x plus 1. This approaches 1 as x approaches infinity. Now, how to find this? We can think of this by looking at the numerator and denominator, and then if they have same power or the same degree, then we just divide the coefficient of the leading term of the numerator by the coefficient or the leading coefficient of the denominator. The leading coefficient of the numerator is 1 and the leading coefficient of the denominator is 1, and that means we have 1 here, which is a value of y as x goes to infinity. We'll elaborate this in a bit, but for now this is what we mean by horizontal asymptote. It's a horizontal dashed line and the vertical asymptote is a vertical dashed line. Now, how to find the vertical asymptote? How to find the vertical asymptote? To find vertical asymptote, we need, if the function is in the written in the lowest term, then it's the 0 of the denominator. So this is 0 of denominator after writing the function in the lowest term. So after simplifying, for example, you may have f of x equals x minus 2 over x squared minus 4. Now this is not written in the lowest terms because we can simplify more. The denominator can be written as x minus 2 times x plus 2, and then you can cancel x minus 2 from numerator and denominator and you get x plus 2. Now you look at the 0 of the denominator. What is the value of x that makes the denominator equal to 0? It's x equals negative 2. So x equals negative 2 is the vertical asymptote. Now, and x equals, now look at the term that was removed from this expression. Look at this. Now x, the 0 of the removed term, I mean x equals 2, the value of x that makes the removed term equal to 0 is called a whole. And that's the main difference between vertical asymptote and a whole. Vertical asymptote, we have a vertical dashed line. That means the function is not defined at this line and we don't have graph. And the whole, by whole we mean the graph looks like this. We have a whole here at some value of x. So we need to write the function in the lowest term. While writing the function in the lowest term, if we cancel some expression, we need to find the 0 of that cancelled or removed expression, and that will be a whole. The 0 of that will be a whole. The remaining expression, we find the 0 of the remaining expression, and that will be the vertical asymptote. Now we have how to find the horizontal asymptote. How to find the horizontal asymptote. Now for horizontal asymptote, as we described here, I said the leading coefficient, if the degree of the numerator is the same as degree of the denominator, we just look at the coefficients, the leading coefficient of the numerator and the denominator and find the ratio of that. So let's elaborate this here, or write it in more general form. If the function is f of x equals p of x over q of x, where p of x is a sub n x to the power n, a sub n minus 1 x to the power n minus 1, up to a sub 1 x plus a node over another polynomial q of x, b sub m x to the power m plus b sub m minus 1 x to m minus 1 up to b1 x plus b node. Now those are polynomials. Now we have three cases. If degree, we just look at the degree of the numerator and degree of the denominator. Now we have the following cases. Either n, degree of the numerator, is greater than m, degree of the denominator, or degree of the numerator is equal to degree of the denominator, or degree of the numerator is less than degree of the denominator. These are the only three cases that we have. Now, if the degree of the numerator is greater than degree of the denominator, then horizontal asymptote does not exist. We don't have horizontal asymptote. If those are equal, the degree of the numerator is equal to the degree of the denominator, we take the leading coefficients and find the ratio of this. So y equals, I mean by y, the horizontal asymptote is a sub n over b sub m, as we've seen in our example here. Now, if the degree of the numerator is less than degree of the denominator, then y equals 0. So these are three cases. Let's take a quick example for each case. For example, here we may have 3x squared minus 1 over x plus 2. Here, no horizontal asymptote. For this case, if we have 3x squared minus 1 over 2x squared plus 1, for example, we have same power, so the horizontal asymptote is 3/2. If the degree of the numerator is less than degree of the denominator, for example, 2x minus 1 over x squared plus 3, as you can see, degree of the numerator is 1, degree of the denominator is 2. That means y equals 0 is the horizontal asymptote. Now, by looking at these, we could find, now we find horizontal asymptote, vertical asymptote. We can sometimes we find another line that looks like asymptote. It's called slant or oblique. So let's write it here. Sometimes we get oblique or slant asymptote. If the degree of the numerator is greater than degree of the denominator by 1. I mean, for example, degree of the numerator is x squared is 2, like x squared plus 1 over x minus 3. Degree of the denominator is 1. So degree of the numerator n is greater than degree of the denominator m by 1. In this case, what should we do? We do the synthetic division. Let's take an example. For example, if we have f of x equals x squared plus 1 over x minus 2, here, as you can see, degree of the numerator is 2, degree of the denominator is 1. So we may have a slant in this case. So what should we do in this case? We do the synthetic division. So what is 0 of the denominator? It's 2. And now for the numerator, we put the coefficients. Coefficient of x squared is 1. Coefficient of x is 0. We don't have x. The constant term is 1. We bring the first coefficient down here, and then we multiply by 2. We put the number here. We add it to 0 to get 2. And then we repeat the process. We multiply by 2. We get 4. Add it to 1. We get 5. So we can write this expression as x plus x plus 2 plus 5, the remainder is 5, but this 5 is divided by x minus 2 actually. So we could write the function in an equivalent form. It's x plus 2 because the coefficients here are 1 and 2, and when we divide x squared by x, that means we get x. We reduce the power of the numerator by 1, so that's linear, and the coefficients are 1 and 2. So 1 is coefficient of x, 2 is the coefficient of, or the constant term. Now we could write the function in another equivalent form, and then we disregard this. Just don't worry about this. Just focus on this expression. So y equals x plus 2 is a slant. If we want to graph it, then we have when x equals 0 we get 2, when x equals negative 2 we get 0. So this line is another asymptote. This is called oblique or slant. So now we have the following asymptotes: horizontal, vertical, and slant. And some of them may exist, some may not exist, and we have whole sometimes. That depends on the details of the rational function. Now, how to graph rational functions? Let's take the first example here, simple example. We want to graph the function f of x equals 2x plus 1 over x minus 3. So first we determine the domain. What is domain of the function? Domain is all the allowed values. So if we have rational function, we just worry about the denominator. What is the 0 of the denominator? Is 3. So everything is allowed except 3. So it's from negative infinity to 3. It's open at 3, union from 3 to infinity. This is the domain. And then we find the x-intercept. What is x-intercept? X-intercept, to find it, we set y equals 0, but y is f of x. So this is 0 equals 2x plus 1 over x minus 3, and then we cross multiply these. We get 0 times x minus 3 is 0, 2x plus 1 times 1 is 2x plus 1, and then we solve for x. When we solve for x, we get x equals negative 1/2. This is the x-intercept. I mean negative 1/2 and 0. Now, what is the y-intercept? For y-intercept, we set x equals 0, and when x equals 0, y equals 2 times 0 is 0 plus 1 over 0 minus 3 is negative third, and that means 0 negative 1/3 is the y-intercept. Now, after finding these, we find the asymptotes. So we have vertical asymptote. What is vertical asymptote? We look at the 0 of the denominator. The denominator is x minus 3. So x minus 3 equals 0. We set that equal to 0. And as you can see, this function is written in the lowest term. So we don't need to worry about wholes. Just the vertical asymptote. And vertical asymptote is 0 of the denominator. So x equals 3 is a vertical asymptote. As we mentioned, no wholes. And then we find horizontal asymptote by using this diagram. As we can see, the degree of the numerator is 1, degree of the denominator is 1, degree of the numerator is equal to degree of denominator, so we just choose the leading coefficients, the coefficient of x with the highest power in the numerator and denominator. So here, what is that? What is that asymptote? So it's y equals, the degree of the numerator is 1, degree of the denominator is 1, so 2 over 1, the coefficient of x in the denominator is 1, so 2 over 1, which is equal to 2. Now we determine where the graph intersects, or whether the graph intersects the horizontal asymptote. So does the graph intersect the horizontal asymptote? We'll see. So the horizontal asymptote is y equals 2. We set this equal to, so the horizontal asymptote is equal to the function, the original function. The original function is 2x plus 1 over x minus 3. And then we solve for x. So we cross multiply these, we get 2x minus 6 equals 2x plus 1. And then we cancel 2x from both sides. We get negative 6 equals 1, and that's impossible. So no intersection. Now, after determining this no intersection with the horizontal asymptote, we plot some additional points. But before that, let's start with the graph. The graph looks like this. This is x, this is y. Now we determine, if we start with the asymptotes. The asymptotes are x equals 3 and y equals 2. X equals 3 and y equals 2. X equals 3 is here. This is x equals 3, a vertical line here. This is x equals 3, the horizontal asymptote. And y equals 2, this is y equals 2, the horizontal asymptote. This is the horizontal asymptote, y equals 2. Now, after drawing these lines, we need to determine the x-intercept and the y-intercept. The x-intercept is negative 1/2, 0. So negative 1/2 and 0, this point here. And the y-intercept is 0, negative 1/3. So this point here. Now, as we can see, the graph looks like this. Now we connect these points, but the graph cannot touch the horizontal asymptote, so we just get closer and closer to the horizontal and vertical asymptote, but we can't touch them. So we graph the function this way. If you want to check, you just take some values of x here. Let's take negative 3. When we have x equals negative 3 and substitute it into the function here, 2 times negative 3, negative 6 plus 1, negative 5 over negative 3 plus minus 3, negative 6. Negative over negative is positive. That means above the x-axis. Now we graph the other part of the function. We need to determine whether the graph is here or here. So how to determine where? I mean here, everything here below because the horizontal asymptote, vertical asymptote split or divide the xy plane into 4 regions: 1, 2, 3, and 4. And as we can see here, the graph should be either here or here for this part. So for the left hand side, it was below here, below the horizontal asymptote and above and to the left of the vertical asymptote. Now to determine the other one, we need to choose some values. So it's better to make a table. That's why it's better to make a table, and that table we make a table or sign chart, either table or sign chart of the function, or plot some points. Some people prefer to plot some points. Let's plot some points here. So we choose, for example, here this is x equals 3, so let's choose x equals 4. X equals 4, the function f of 4 is, the function was 2x plus 1 over x minus 3. 2x plus 1 over x minus 3. So we substitute x equals 4, we get 8 plus 1, 9. 4 minus 3 is 1, so it's 9. So this point here, 4, has image 9. 9 is somewhere here, so that means we are in the first quadrant. Here. So we graph the function here, we graph it this way, because it cannot touch the vertical asymptote and it doesn't touch or intersect the horizontal asymptote. So the function consists of two pieces. So this is for 9 as a point. This is how we graph these functions, the rational functions in general. Let's take another example. We want to graph the function f of x equals x squared plus 1 over x minus 2. Now to graph this function, we find the domain. What is the domain? Domain is all values of x, all allowed values of x, so everything except x equals 2. So I mean, here we have x equals 2, but anything else is okay. Negative infinity to 2 union 2 to infinity. And then we find the x-intercept by setting y equals 0, and that means 0 equals x squared plus 1 over x minus 2, and then cross multiply these, you get x squared plus 1 equals 0, and that means x squared equals negative 1, and that's impossible. You can't have a value whose square is negative, so there is no horizontal asymptote, no x-intercepts. Now what about y-intercept? For y-intercept we set x equals 0, and that means y equals, just substitute here, x equals 0, you get negative 1/2. So it's 0, negative 1/2. We have the graph intersects the y-axis at negative 1/2, but it doesn't intersect the x-axis. Now after that, is there any holes? No. This is written in the simplest, the lowest term, so no holes. Is there any slants? Yes, because the degree of the numerator is 2, degree of the denominator is 1. The difference is, this is n, this is m, degree is 1. N is greater than m by 1. So this is 2, this is 1. So that means we need to use synthetic division to divide these. We find the 0 of the denominator. 0 of the denominator, I mean the value of x that makes the denominator equal to 0, which is x equals 2. And then we look at the, we need to determine the coefficients of the numerator. We have x squared plus 1, the coefficient x squared is 1, the coefficient of x is 0, the constant term is 1, and then we bring this down here, multiply by 2, add to 0, multiply by 2, add to 1. We already did this when we introduced examples for slants. Now this is the leading coefficient of x, this is, or the coefficient of x, and this is the constant, and 5, this is the remainder, 5 over the denominator. The denominator is x minus 2. So 5 over x minus 2. So we could write the function in an equivalent form. And as we mentioned, just disregard this, the fractional part, and just use the linear part, x plus 2. So now we are, the last thing to check, the intersection with the horizontal asymptote. Is there any intersection with the horizontal asymptote? Since horizontal asymptote, does not exist, that means there is no intersection. Now we graph this function. We start with the slant. The slant is x plus 2. So we graph it here, x plus 2, that means when x is 0, it's 2, and at negative 2 is 0. So we have a slant which is an asymptote. Now we have a vertical asymptote here. The vertical asymptote was, I think we need to find the asymptote, so I skipped this. So what is the horizontal asymptote? The horizontal asymptote, let's start with the vertical asymptote. The vertical asymptote is the 0 of the denominator. 0 of the denominator is x equals 2. we set the denominator equal to 0, and then we solve for x. This is the vertical asymptote, and then we find the horizontal asymptote. As we can see, degree of the numerator is 2, degree of the denominator is 1, so n is greater than m. That means does not exist. We don't have horizontal asymptote, but we have vertical asymptote at x equals 2. So at x equals 2, this is x equals 2, we have a vertical asymptote. Now we graph the function. Now to graph the function, we need to determine the x-intercepts, y-intercept. We don't have x-intercept, but we have y-intercept at 0, -1/2. So 0, -1/2 here. So this is 0, -1/2. And now the graph looks like this. It's closer and closer to asymptotes. Now what about the other part? So we have 4 regions. This, and this. For this one, we already draw the line or the function, the curve. And now, since it's here below this line, it cannot be above the line as well, the slant. Now, to the right of x equals 2, the vertical asymptote, we need to check some point here. Let's check the point 3 and see if it's below or above the slant. Now now this slant, let me write it here, it's x plus 2, this is slant. Now when x equals 3, what is the function? The function is, we know that f of x is x squared plus 1 over x minus 2. So when x equals 3, we find the image. It's 9 plus 1, 10 over 1, which is 10. That means it's somewhere here. So this point is 310. So the graph looks like this because it cannot touch the asymptotes, the vertical asymptote or this slant. So the graph consists of, let's use same color here as the other part of the function. So this is the graph of the function. It consists of 2 curves, disjoint curves or separate curves of the function. Now we have the last example. Let's discuss the last example here in this video. If we want to graph the function f of x equals 3x squared plus 9x minus 12 over x squared plus x minus 2 all minus 4, we start with, if it's not easy to determine the domain, don't worry about that. So let's start with x-intercept. We set y equals 0. When y equals 0, this is y. 0 equals this expression. And then we add 4 to both sides. We get 4 equals 3x squared plus 9x minus 12 over x squared plus x minus 2, and then we cross multiply this by this, and this times this. We get 3x, this times 1 is 3x squared plus 9x minus 12 equals x squared plus x minus 2 times 4, it's 4x squared plus 4x minus 8. And then we solve for x. So let's subtract 3x squared from both sides. We get 9x minus 12 equals x squared plus 4x minus 8. And then we subtract 9x to get negative 12 equals x squared minus 5x minus 8, and finally we add 12 to both sides. This becomes 0, and we write x squared minus 5x plus 4 is equal to 0, and then we solve this for x, so we can factor this. It's x minus 4 times x minus 1 equal to 0, and then we get two solutions, x equals 4 or x equals 1. But as we can see, we need to determine whether these 2 points belong to the domain or not. The point 4, yes, because if you plug 4 here in the denominator, you get 4 squared plus 4 minus 2 is not equal to 0. But if we plug x equals 1, we get 1 squared plus 1 is 2 minus 2 is 0. This value makes the denominator is equal to 0. That means we just cancel it because this does not belong to the domain. Now, after determining the x-intercept, so the x-intercept is 4, 0. This is the x-intercept. Now we find the y-intercept by setting x equals 0. That means y equals, if we substitute y equal x equals 0, this is 0, this is 0, negative 12, 0, 0 over negative 2 minus 4. So negative 12 over minus 2 minus 4. This is 6 minus 4, which is equal to 2. So 0, 2 is the y-intercept. Now after that, we try to find the asymptotes. Let's start with the vertical asymptote. For vertical asymptote, we need to simplify the expression first. So our function is f of x equals 3x squared plus 9x minus 12 over x squared plus x minus 2 all minus 4. So we need to simplify this to write in the lowest form first. So this becomes 3 times, we can take 3 as a common factor. As you can see, this is a common factor or multiple of the numerator. So, or factor of the numerator. So we have x squared plus 3x minus 4 over, what about the denominator? The denominator can be factored as x plus 2 times x minus 1. Now minus 4 here. And then we can factor the numerator. The numerator becomes, now we already have 3 here, x plus 4 times x minus 1. So we can write this as 3 times x plus 4 times x minus 1 over x plus 2 times x minus 1 all minus 4. So this is f of x. Now we cancel the like term, I mean x minus 1, but when we cancel this or remove this, we have the 0 of this, the value of x that makes the removable expression equal to 0 is called a whole. So we have a whole at x equals 1, and that value of that whole is 1, and we substitute 1 into the function, what is left here. So it's 3 times 1 plus 4 over 1 plus 2, which is 15 over, I mean minus 4 here. 15 over 3 minus 4, and that's 5 minus 4 equals 1. So 1, 1 is the whole. Now what is the vertical asymptote? After cancelling x minus 1, we get 3 times x plus 4 over x plus 2 minus 4. So what is the value of x that makes the denominator is equal to 0? It's x equals negative 2, and this is written in the lowest term, so this is a vertical asymptote. Now what is the horizontal asymptote? This is very easy. We just set we just look at the degree of the numerator, degree of the denominator to determine this. So the function is 3x squared. 3x squared, this is the function. 3x squared plus 9x minus 12 over x squared plus x minus 2 all minus 4. The degree of the numerator is 2, degree of the denominator is 2. So we just look at the coefficients, the leading coefficients. The leading coefficients are 3 and 1. So it's 3 over 1, but we have negative 4 here, minus 4, and that's equal to negative 1. So the horizontal asymptote is y equals negative 1. So we determined the horizontal asymptote. Now we need to determine whether the function intersects the the horizontal asymptote. So intersection with the horizontal asymptote, I mean y equals negative 1. We set the function equals to negative 1. The original function is equal to negative 1. So negative 1 is equal to 3x squared plus 9x minus 12 over x squared plus x minus 2 all minus 4. And then we add 4 to both sides. We get 4 minus 1 is 3. And then we cross multiply these. So we get 3x squared plus 3x minus 6 multiplying this by this equals 3x squared plus 9x minus 12. And then we subtract 3x squared from both sides to get 3x minus 6 equals 9x minus 12. And then we subtract 3x from both sides to get negative 6 equals 6x minus 12. And then we solve for x. We add 12. And then we get 6x equals 6. That means x equals 1. But as we can see, this does not belong to the domain. So we don't need to worry about this because we have a hole at this. So we don't have intersection with the horizontal asymptote at this point. Now we graph the function. So the graph looks like this. So this is x-axis, this is y-axis. And we start with the asymptotes. So we have vertical asymptote. What is the vertical asymptote? It's x minus 2, x equals minus. What is the vertical asymptote? It's x equals minus 2. So x equals minus 2 is the vertical asymptote. Now what is the horizontal asymptote? The horizontal asymptote is y equals negative 1 so y equals negative 1, and then we determine the intercepts. We have what are the x-intercept and y-intercept. So here we have the x-intercept is x equals 4 or 4, 0, and the y-intercept is 0, 2. This point here, 4, 0, and 0, 2. 0, 2 is here. So the graph looks like this from here. Let's use a different color. The graph looks like this here. And by looking at the graph, we know that there's a hole at 1, 1. There's a hole at 1, 1. So here we have 1 1, so we make a hole here, so the function is not defined here, so the graph looks like this. At 1 1 we have a hole, and then we continue the graph. Now there's another part of the graph here, so we guarantee that the graph cannot be here, the other part of the graph, because we already covered the upper part, or we graphed it in the upper part for the values of x. And now we choose some values, plot some points. So we choose some points here. Let's choose -3. When x equals -3, we need to determine f of -3. So this is 3 times -3 squared plus 9 times -3 minus 12 over -3 squared minus 3 minus 2 minus 4. Now this is 9 times 3, 27, minus 27 minus 12 over 9 minus 3 minus 2 all minus 4. This is 0. We get -12 over 9 minus 3 is 6 minus 2 is 4 minus 4. This is -3 minus 4, which is -7. So at -3 we have -7. That's the image. -7 is somewhere here. So we have -3, and let's say here -7. So this point is, that means the graph will be in this quadrant. So the graph looks like this. Now this is how we graph these functions, the rational functions.